Hello maths fans, Dr Tom Crawford here at the University of Oxford, and today we're talking about Taylor's theorem, quite possibly one of the most useful results in all of maths. To see where Taylor's theorem comes from, let's start with a general example. Suppose we have a function f of x and we want to express this function or approximate this function as a polynomial. So let's call this Pn of x. And the n here symbolizes that the highest power of x we're going to consider is x to the power n. And at this point, f here can be absolutely any function you can think of as long as it's differentiable. Now what we're going to do is actually define Pn of x by expanding around the point A, where A is some general point. So if we were to do this, we could say that Pn of x is equal to A0, our constant term, plus A1 multiplied by x minus A. So this is A1 to symbolize that this is our coefficient on the linear term, the linear power of x, plus a2 times x minus a squared, and this will continue up to an times x minus a to the power n, and remember we're stopping at the power n because we have fixed our polynomial Pn to be of maximum degree n. Now we have a choice about how to define our coefficients, these ak coefficients. And what we're going to do, and this is really the clever part, is we're going to pick our coefficients such that the kth derivative of our polynomial, where k could be 1, 2, 3, first, second or third derivative, the kth derivative at the point A, which is, remember, the point we've expanded around, we want this to be equal to the kth derivative of our function f at that point A. So we are imposing this condition. So we're looking for this, so we're trying to find this polynomial. And in order to help us determine the coefficients, we're going to set this to be true. So what this means is to actually calculate these coefficients, we can calculate or compute some of the derivatives of our polynomial and then set them equal to the kth derivative of this function f at the point A. So let's try that. The first derivative of Pn, so Pn prime of x, this is simply, well, we lose the a0, we lose the constant term, we differentiate this and just keep the a1, we bring down the 2, so it would be plus 2 lots of a2 times x minus a, and then we continue in a similar vein, and the term on the end would become n lots of an x minus a to the n minus 1. So in each term, we're just bringing down the power, reducing the power by 1, and from the chain rule, the x is only multiplied by 1, so there's nothing to carry from the chain rule. So if we also calculate the second derivative, then the a1 term now disappears, so we get 2 times a2 plus dot dot dot, and then at the end here we're now having n times n minus 1 times x minus a to the n minus 2. So these are the first two derivatives calculated explicitly. Now if we think more generally about what's going to happen here as we continue to take more and more derivatives of our approximating polynomial, there's going to be a pattern. And we can see this, in fact, in these first two that we've gone through explicitly. So if we continue and consider the kth derivative of our polynomial, and remember we're interested in the kth derivative, a general derivative, because that's how we're going to fix our coefficients, these AI coefficients. So the kth derivative. Now, the first few terms will disappear. So the constant term has gone, the linear term has gone, the quadratic term has gone, all the way up to the term that had an x minus a to the k. Anything before that point has been differentiated away because we've differentiated so many times, more times than the degree of the polynomial. So all those first few terms will vanish. So the first one that doesn't vanish is actually going to be the term that had x minus a to the power k. So the ak would be the coefficient, and then we've differentiated down k times. So that's a k, and then again k minus 1, k minus 2, and we're going to go all the way down to 1. So we've actually got k factorial. Now the next term along is going to be ak plus 1. And again, we had x minus a to the k plus 1. We differentiate k times. So I bring down a load of factors. So I bring down k plus 1, and then a k, and then a k minus 1, and we go all the way down to 2 in terms of that coefficient. And then we're left with an x minus a. And then we can continue for the remaining terms. The most important thing here to spot is there will always be at least 1. The power of this will actually increase, but there's at least a single x minus a term in all of the others apart from this first one, and we'll see why that's important in just a second. But the very last term, so I've done k derivatives, so I'm left with, so we've got an an, we've brought that down, so it's an x minus a to the n minus k, having done k derivatives on that polynomial term. Then we're going to have, it's going to look like an n minus k factorial on the bottom with an n factorial on top. So I've made a little bit of a mess of writing that, but you've got an n factorial term over an n minus k factorial, I believe is what you'll end up with there. Now, I'm not too fussed about exactly how I've written that because that actually isn't important. Because here, what we're interested in, or the rule that we're using to determine these coefficients, is we want the derivative at a for our approximating polynomial to be the same as the derivative at a for our function f. Depending on whatever function f we input, this will of course change, but this won't, because this is always a polynomial of this form. So when we evaluate this expression here at x equals a, what's going to happen is the first term stays because it's a constant, but the next term we've got x minus a, but x is now a, so this is 0 and disappears. And all the other terms after it have at least a single power of that, all the way up to this last one, which again is 0. So all those other terms vanish, which is why I wasn't too fussed about how neat my final formula was. We don't actually care. This is the important term. So what we can say now is if I plug in x equals a, as I've done here, I just get this. So we need fk of a needs to be equal to ak times k factorial. So this is in fact what we now need to solve to get our coefficients ak, and of course they will differ depending on the function f that we're trying to approximate. So we can rearrange this to say our coefficients ak are simply the kth derivative of our function f divided by k factorial. So this is the formula for each of these coefficients, and if we plug that in up here, we will in fact get Taylor's theorem. Substituting for the coefficients into our polynomial formula, we have this setup. So we're trying to approximate any differentiable function f by an n-degree polynomial, and we've chosen our coefficients so that f and our polynomial agree on k derivatives at the point A. This is the formula we have derived, and now what we can do is actually appeal to a result from analysis called Cauchy's mean value theorem. So I'm not planning to go through the full proof of this because that would be for an analysis course rather than a calculus course, but using something called Cauchy's mean value theorem, we can actually say that because these functions agree at these various derivatives, and this will be true all the way up to k equals n, because they agree on these n derivatives at this point A, we can say that they are in fact almost the same. So what we mean by almost the same is Pn will be exactly f provided I continue this pattern forever. So if I allow the degree of my polynomial to increase further and further, I get a better and better estimate or approximation for the function f. So Taylor's theorem, which is ultimately what we're trying to get to here, basically says that for a differentiable function f, and this can be any function f, and we'll see various different interesting functions in some examples shortly, we can say that f of x is approximately equal to this Pn of x. So it's approximately equal to f of a plus f prime of a times x minus a plus dot dot dot, and then we continue with f n of a x minus a to the n over n factorial plus dot dot dot. And what Taylor's theorem tells us is this approximation, writing any function f as a polynomial, it gets better and better. It's more and more accurate the more terms we take. So the more derivatives of f we can calculate, and therefore the higher powers of x that we include in our formula, allows us to express any function f as a polynomial. That is the power of Taylor's theorem and Taylor expansions. As you can see, when using Taylor's theorem in practice, we need to be able to calculate several derivatives of the function f that we are trying to approximate. And this is where the Maple Calculator app is a real lifesaver. Simply enter the function that you need to differentiate, and the app will automatically do the derivative for you. And to really assist with your learning, you can click on the Steps button to see a full breakdown of how the derivative was calculated. Download the app for free and try it out for yourself. Now that we've derived our formula for Taylor's theorem, let's try a couple of examples to see it in action. First, let's start with a function whose expansion some of you may already be familiar with. So we're going to look at cos of x. Don't worry if you are not familiar with the expansion of cos, because we are going to calculate it now, but if you have seen it before, this is perhaps an alternative way of deriving that power series. As well as having our function f, we also need to decide where we're going to do the expansion. So here, I'm interested in expanding around x equals 0. So what this means is we are trying to approximate our trigonometric function cos, and we want to know what does that look like for small x. So when x is near to 0, can we write down a polynomial expression for cos of x? And to do that, we're going to just use our Taylor's theorem, our Taylor expansion formula at the top of the board. So we need to know f of 0. So that's quite straightforward. That's cos of 0, that's 1. We also need to know some derivatives. So f prime of x our first derivative of cos is going to be minus sine of x. So therefore f prime of 0, well, that's naught, because sine of 0 is 0. Now, the second derivative, f double prime of x, well, that's the derivative of minus sine, so that's minus cos of x. So f double prime of naught is minus 1, because it's minus times cos of 0. Now, our third derivative, that is the derivative of minus cos, so that comes back and gives me a sine of x. So therefore, my third derivative at 0 is again naught. And then the last one I'm going to do is the fourth derivative, because what happens here, when I do f4 of x, is the sine differentiates to give me back cos. So we've actually gone full circle back to where we started. And f4 of 0 is once again 1. So plugging all of these values into Taylor's theorem, we can say that cos of x is equal to, first of all, we want f of 0, so 1. The next term is 0, because the derivative is 0 there. Then we get minus this term, so we've got a minus 1 over 2 factorial. And then on the numerator, we've got x minus a squared, but a is 0, so that's just x squared. Then the next term would be x cubed, but that's 0. Then we get the x fourth with a plus, so plus x to the 4 over 4 factorial. And now because the pattern repeats, f to the 5, 0, f to the 6, I know is going to be minus 1. So I'll get a minus x to the 6 over 6 factorial, and it would be plus x to the 8 over 8 factorial minus dot dot dot. Now you may have noticed that I've written an exact equals sign, and that's because I'm illustrating through this ellipsis, through the dot dot dot. This is showing that this will continue. So this pattern of alternating signs on even powers will continue. And as Taylor's theorem tells us, it is exact if we continue forever. So the one I've written at the top, I've written is approximate because I stopped, but we know that if we continue forever, then it is indeed exact. So if I continue this forever, this is exact. So what we can actually spot here, because of this loop and this repeating pattern, we can say that this is equal to the sum. We want the even powers of x. So if we say we go from n equals 0 to infinity, and then we need x to the 2n, then that will just pick out the even powers. So I'll get x to the 0, which is 1, and then I'll get x squared. So we need to be dividing by 2n factorial, because the factorial on the bottom is the same as the power. So that's over 2n factorial. And then we have this alternating sign. So what I actually need here is a minus 1 to the n. Because then when n is 0, that's a plus. When n is 1, it's a minus. When n is 2, it becomes x to the 4, and then it changes. So this is in fact the infinite sum, or the power series expression for cos of x that some of you may have seen before. But again, don't worry if you haven't. There are lots of different ways to derive this, but we have shown here that we can get it from Taylor's theorem and from the Taylor expansion of cos. And we know that it's exact because if we continue this forever, then it will indeed be exact by Taylor's theorem. But of course, we can stop. I could have stopped here and said it is approximately equal to 1 minus x squared over 2 for small x. Now let's try a slightly trickier example. So we're going to do the expansion of the function f of x is the natural log of 1 plus sine of x, and we're going to expand this for small x. So we want to expand around x equals 0. Now this is a more complicated function and also is not a standard function, which means it does not have a known power series expansion, unlike the last example with cos. So here we really do need to use Taylor's theorem in order to get our approximation as a polynomial for small values of x. Once again, we begin by calculating f of 0. So here this is log of 1 plus sine of 0. Sine of 0 is 0. So that's log of 1, which is 0. Now we need some derivatives. So f prime of x. We have log of a function. So for the derivative, we do 1 over the function, 1 plus sine x. And then we differentiate the function, the thing inside the log. So the derivative of sine x gives me cos x. Now we want to know what is f prime at 0. So cos of 0 is 1, sine of 0 is 0, so that's just 1. Now for the second derivative, which of course is a little trickier, and I'm going to calculate this using the product rule because I prefer the product rule over the quotient rule. So doing this as a product, I need to ignore the cos. So we have a cos x, and then I want to bring down the minus 1, so it becomes a minus. I get 1 plus sine x all to the minus 2, and then I get another cos x from the derivative inside that bracket. So I believe I get minus cos squared x, 1 plus sine of x squared, and then I now need to ignore the denominator. So that's a 1 plus sine x on the bottom, and I have to now differentiate the other term, which is the cos x. So that gives me a minus sine x. Now I want to know this at x equals 0. So again, I plug that in, f double prime of 0. What we're going to get is this term disappears because sine of 0 is 0, so that whole thing vanishes, and this is going to be minus 1. So that's just minus 1. Now for the third derivative, I'm going to use the Maple Calculator app on my phone. So if I open up the app and then click on the camera icon, it's asking me to frame my equation. So if I do that, make sure it's all inside the box and take a photo, then the equation will now appear on screen in my app. So not only does the expression appear in the app, but I can click on the differentiate with respect to x tab, and it will give me the derivative. So it gives me the derivative of f double prime as written on the board, so therefore that's the third derivative of f which I'm looking to calculate. And I can go even further, in fact, and click on the steps icon, as I mentioned earlier in this video, and it will actually give me a step-by-step breakdown involving the quotient rule, involving the chain rule, various other things to get to the solution. So not only can you check your answer, but you can also see a step-by-step breakdown of how to get there. Copying the formula from my phone onto the board then, and just as with all of the other derivatives we've calculated, we want to know the value of this at 0. So plugging that in, we can say that f triple prime of 0 is going to be equal to, well, this first term disappears because sine of 0 is 0. This gives me a 2, because it's 2 times 1 cubed over 1 cubed, so that's just 2, and then minus 1 over 1. So it's 2 minus 1, so it's just 1. Seeing as I've just about ran out of space and these derivatives are getting more and more complicated, let's stop at this point and formulate our approximate polynomial for log of 1 plus sine x. So, following Taylor's theorem, we can say that the log of 1 plus sine x is approximately for x small, meaning x near to 0. It's approximately equal to f of a, well that's 0, plus f prime, so plus 1 times x minus 0. So it's approximately equal to x, it's going to be our first term. Then f double prime is minus 1, so minus 1 over 2 factorial, so minus a half x squared. And then we've got a 1 for our third derivative over 3 factorial, which is 6, and we've got an x cubed. So plus x cubed over 6. So our formula for log of 1 plus sine x, we can say this is approximately equal to x minus x squared over 2 plus x cubed over 6 whenever x is small, i.e. whenever x is near to 0. So there you have it, Taylor's theorem for approximating functions as polynomials. As I said at the very beginning of the video, an incredibly useful technique which is used in almost every area of applied maths. If you want to keep practicing with some more questions, then head over to Maple Learn and take a look at the worksheet which I've put together. You can access the exercises for free by clicking on the link in the video description. Thank you everyone for watching. Please do remember to subscribe if you've enjoyed the video, and I'll see you all soon. Take care.